first 5 minutes, usually questions for those who joined us lately, or if you have a question on the last time lecture, aerodynamics. Today we are going to wrap up our aerodynamics introduction, finish what we need. So also probably see if you have questions. And I have.
Doctor?
Ayuh.
Sorry, but what did you say about the thing that you have access for 3 weeks?
No, if the videos, they are there on Blackboard, just like the lectures, the slides, you can download, you can open and so on. But some of your colleagues in the other section had a problem with that video of lecture number 1, or sorry, lecture number 2. So if you have a problem with it, it's also saved on Teams. Chats of the Teams group, it's there, automatically saved after we are done, like 5 minutes. After we finish, it's there for 3 weeks. So you can download it from there as well. Okay. Type. I hope you don't have questions because you have read the lecture, because we are coming to our first homework pretty soon. So next time we'll be assigning our first homework. So you have some reading to go through. Textbooks. Shall we raise our hands if you have the textbook? I checked it a time ago. Can you please raise a hand just to know how many textbooks we have? Because it's important to know before I assign the homework. Still too few. Okay, I'll put it, I'll try to make it in a way that you will not need anything beyond the slides in the homework. Okay, at least the first one, until you receive your textbooks. The slides should be enough for answering the homework. Okay, thank you for raising your hand. You can take this out. Okay, so let's move on. If we don't have a question, I'd like to continue and wrap up our aerodynamic introduction. What we had last time, we were covering chapter 2, and we stopped short of the airfoil families. And it's important that you be familiar with these families because you will pick from them. You will come in like 4 or 5 weeks from now, and when you design the wing, you will say, I will pick airfoil 0014, or I will pick a certain airfoil. So you should be familiar with them so that you can pick them. You cannot pick something if you don't understand what they are. So it's very important for us to know what does the meaning, what does the name of the airfoil mean. So in order to do this, we will first understand what are the characteristics of the airfoil. We talked about the camber last time, the maximum thickness. We talked about the chord, the line connecting the leading edge to the trailing edge. We have also the maximum thickness here, the camber, the camber, the maximum distance between the center line and the horizontal, or the chord in this case, and the maximum thickness. Also is important, where is that camber? If this camber has a small value, increases, then decreases, the maximum value of it, where does it occur? Does it occur at the very front of the airfoil? It will have a shape, or it's in the middle or in the back. This will change the shape of the airfoil and of course the aerodynamic characteristics. So let's see these values for different families of airfoil. Yes?
Doctor, I have a question.
Yes.
What's the difference between the chord C and chord line?
C is the length of the chord line. So the chord line is, let me go back to the slide. You see this chord line is the reference line that we have. C is that length, the dimension. So C is like 5.3 centimeters, 6 meters, whatever. Okay, so it's the dimension. Okay.
Okay.
So over the years, engineers have developed several families of airfoils. One of them is the 4-digit series. It's a very famous series, particularly for slow aircraft. It was developed by NACA, and the naming of them is just like this. It has 4 digits. The last 2 digits tell you what's the maximum thickness percent of the chord. So this 12 here tells me that the maximum thickness, which is this distance, is 12% of the chord C. If the chord C is 1 meter, this is 12 centimeter. If the chord is 2 meter, this is 24 centimeter, and so on. So it's 12%, 0.12 of C. The first digit tells me the camber, the maximum deviation of the center line from the chord line. What is this distance? This 2 tells me that it is 2% of the chord. So if the chord is 1 meter, this distance is 2 centimeters in here. The 4, or the second digit, tells me the position of the camber, but it doesn't tell me directly. 4 means it's 40% of the chord. So this maximum camber occurs at a position that's 40% of the total chord, or 30% or 20%, whatever. So this is how it's named. Okay, so if I have an airfoil called 2414, I will know it's just like this one. It's 2% at 40% of the chord. But this 1.2, instead of 1.2, it will be 1.4. That means it's going to be a thicker airfoil. So it will go above like that. It's going to be a thicker airfoil. And of course will generate more lift. The thicker the airfoil, the more lift it will generate. Okay, so this is basically how it's numbered, how this 4-digit series is numbered. Now there is another series, another family of airfoils called the 5-digit series, and it's numbered differently. Typically, a 5-digit series will be used for slightly faster aircraft. So general aviation, business jets, even transport aircraft. In the transonic regime, they could have a 5-digit series. Okay, and again, the numbering has its rules, and this is how people agreed to number the airfoil, so that once I know the name of the airfoil, I have everything about it. The last 2 digits are still the maximum thickness percent. So this 12 means 12%. Maximum thickness, 12% of the chord. But the first digit doesn't mean now the camber. It means some aerodynamic characteristics of the airfoil. This 2 means that the design lift coefficient is take that number and multiply it by 1/2. Now, why it's so complicated? Well, they agreed to do so to cover a wider range of airfoils. So taking the 2 multiplied by 1/2 makes it 3. That means CL is 0.3. Okay. So the first number has an indication of the CL. The more the number that we have here, so if I have a 5-digit series that start with a 4, I know it will generate more lift than a 5-digit series airfoil that start with a 2, because the first number represents the design lift coefficient. It goes up with the design lift coefficient. The second and third digits, the 30 here, means the position of the maximum camber, just like it was in here, but with a twist. This 4 here meant that the maximum camber is at 40%. This 30 here means that the maximum camber is at 15%, half of that. Okay, so the 30 means it's 15%. This would allow like fractions of the camber to be included. This numbering system allows me to put the maximum thickness at, let's say, 17%. I cannot do that here, because here it's in tenths of the chord. 40%, 30%, 20%. But here I have the capability of having 15, 16, 17, and so on. So if this is 34, maximum camber will be at 17% of the chord. Are you following?
Yes, yes.
Okay, so I have an airfoil for you. Airfoil 0012. What do you think it's going to look like? Would it be thicker than this airfoil, or it has the same thickness?
Same thickness.
0012.
0012.
Again,
0012.
same thickness.
Same thickness. 0012. Will it be cambered up or down?
In the middle. Down.
In the middle. No.
Yeah.
0, the first 0 means the camber is 0, so it will not camber up or down. That means that it's going to be, this dotted line will be here along the solid line. That means the airfoil is going to be symmetric, right? Because this dotted line is the center line between the top and the bottom. The distance from here to the top is the same as the distance from here to the bottom. So if the dotted line is along the solid line here, that means the airfoil is going to be symmetric. So here is the airfoil 0012. It's a symmetric airfoil. Okay, so any 4-digit series airfoil starts with a 0 is a symmetric airfoil. Symmetric airfoil are important in a sense that they have 0 lift at 0 angle of attack. So if you put an airfoil like this in air, it will generate 0 lift, no lift whatsoever. If you increase the angle of attack, it will start to generate the lift. Okay, so that's the 0012 we were talking about. It's a symmetric airfoil, generates 0 lift at 0 angle of attack. Okay. The last family that we'll see is called the 6 series, and there is a typo on the slide on Blackboard. I think I'll correct that. It's written 6-digit series. No, it's not 6-digit series. It's still 5-digit series, but it's called the 6 series family. 6 series because it always starts with a 6. When NACA developed this family, they designated the first digit as 6. It doesn't mean anything other than that it's a member of that family. It's not thickness, it's not camber, it's not lift coefficient. The 6 series is used for even faster aircraft. So if you have Boeing 737, 757s, 67s, 777s, Airbus, there is a chance in an aircraft of this category to have a 6 series airfoil. Although aircraft manufacturers will have their own airfoils, they will develop their own families, but you can have such an airfoil on this aircraft. The second digit, the 4 that we have in the second digit, doesn't mean the location of the maximum camber. It means the location of the minimum pressure. So the 4 means the minimum pressure of 40%. Why is the minimum pressure important on an airfoil? When I say the minimum pressure is here, for example, why would that be important?
Can you repeat the question, Doctor?
The question is in the 6 series family, the second digit means the location of the minimum pressure. So my question to you was, why it's important to know that the minimum pressure of this airfoil, for example, is at 40% of the chord. This 4 says it's 40% of the chord. So the minimum pressure will be, let's say, here. Why would that be important? From a design
maybe to know where to strengthen the material covering the airfoil, maybe.
Where to put?
Maybe to find out the best angle of attack.
Okay. Where is the maximum? How is lift generated on the airfoil? Because of the low pressure on the upper surface, you will have the suction force upward. That's the lift, right? So this 4 will tell me that the maximum upward force is going to be at 40%. So if I draw the pressure distribution, for example, or the lift distribution, it will look like this. It will start from 0, go up, and then it will go down. Okay, so it tells me where is the maximum lift. This has implications, as both of you mentioned. It has implications on the structures, where to have the spar, for example, where to put the spar inside the airfoil to strengthen it. Okay, and it has implication on the value of the total lift as well. Okay, so that's why the second digit here means the minimum pressure. These third digits gives me the design lift coefficient. So the higher the number here, the higher the lift it will be generated by the airfoil. Okay, so 2, 3, 4 means the lift coefficient is 0.2, 0.3, and 0.4. So now you have the families. When we start designing in week 5, inshallah, or 6, I would say week 6, and you start designing the wing, you will have to choose the airfoil from these families. Okay, so that's why it's important to be familiar with them. Any question? Okay, the next point, we're gonna move on from the airfoils. So far, all our discussion have been for the airfoils, which are basically two-dimensional wings. Wings extend from infinity to minus infinity. Span is infinity. Now let's move on to three-dimensional wings, finite wings, where the actual wings, where the wing has a start and an end. And the question, would the lift coefficient of that wing be the same as that of an infinite wing? Let me put it in another way. Would the lift generated by a wing of finite length be the same as the lift generated by the airfoil that extends from infinity to minus infinity? And
No.
the answer,
No, I don't think so.
It will be
Uh,
less.
it has to be less, and the reason for this is the three-dimensional effect. The three-dimensional effect, for those if you haven't taken E20, means since air is coming to the wing at a certain angle of attack, moving up and moving down, then we are going to have high pressure below the wing, low pressure above the wing. So if you have air that's confined, very high pressure, very low pressure here, and the wing does not extend from infinity to minus infinity, it has a finite length, naturally the high pressure air will tend to move upward. It's just like you are pushing on the air down. So it needs to move upward. But whatever goes up will go down again. And then it will move up, down as the wing moves through the air. So as the air continues to move up and down, it will start to circulate and move away from the wing in what we call the wing tip vortex. So for this wing tip vortex, it has some desirable and some undesirable effects on the aerodynamics. In a sense, it will reduce the angle of attack because it will go down. The air will have a downward component. It will generate more drag, which is called induced drag. Okay, and it will generate disturbance in the air behind the wing. And this disturbance is considerable. If you consider a relatively small aircraft, the Boeing 727 here, a relatively small aircraft, you see the size of the tip vortices start to increase as you go beyond the wing tips, and they are considerable. They affect aerodynamics considerably in here. If this was a larger aircraft, a 747 for example, this would even be bigger, and that would disrupt the flow on any aircraft that's coming behind that one. And that's the reason why there is a separation in takeoff timings between aircraft. If you are on board a 737 and in front of you on the taxiway and on the runway a 747, your aircraft cannot take off right after the 747. You have to wait for about 3 minutes, 4 minutes before your aircraft takes off, so that these wingtip vortices have calmed down. Okay. So let's study more these three-dimensional effects. How would the finite wing affect the lift and drag? First, we have something that's called the downwash. And the downwash, in a sense, is the downward motion of air as it moves behind the wing. When air is coming, let's say it's horizontal, it will start to move up a little bit. It's not gonna move to this airfoil and then start moving up. No, that doesn't happen in nature. Nothing happens abruptly like this. It's just like cars moving in lanes. They will start to have to move up a little bit to make room for the wing and then go down. So although air was coming horizontally after the wing, it has a downward component. Of course, way after the wing, it will move horizontally again, as it was before. But right after the wing, for a certain distance behind the wing, air has a downward component. You see, it's going up and now it's going down. Any surface you put here will see the air going down a little bit. What surface do you have behind the wing in an aircraft?
Horizontal tail.
Horizontal tail. So any horizontal tail in this area will not see the air at the same angle of attack of the wing, but it will see it at an angle of attack that's slightly less than that because of the downwash. Okay? So the downwash, which is induced by the wingtip vortices as well, means that the angle of attack on any surface will be reduced a little bit by the downward motion of the air. Okay, so the effective angle of attack is alpha minus alpha downwash. For the wing, it's alpha minus alpha induced. You have to take that downward component out of your equations. Okay, let me ask you a question. Have you seen the Typhoon? The aircraft Typhoon? Of course, probably I've seen it. What do you have in front of the wing in the Typhoon?
You mean on the head of the aircraft?
Yes, near the nose, right?
Yes, small wings.
Yes, it's a small surface. Let's not call it wing. What do you call that surface?
Tips, I think.
Yeah, maybe small airfoil or something.
A small
airfoil, maybe.
Airfoil is the two-dimensional. It's the shape that we have here. Once it starts to have 3D, it has a name. Let me bring that picture here. Let's bring it here. So here's the Typhoon. We have that surface. Where is the horizontal tail? What's the tail of the aircraft?
In the front, Doctor.
In
The front, near the cabin of near the pilot here.
Yes.
It's the one in the front.
It's the one in the front. So the horizontal surfaces don't have to be behind the wing always. They can sometimes be in front of the wing. If they are behind, it's a tail. If it's front, it had a different name. So that we don't say a small wing or the tail in the front, because tails never are in the front, right? This is called a canard. Okay, so a Typhoon doesn't have a tail, a horizontal tail. It has a canard, and it does exactly the same thing. If you have a tail in the back, the main reason why do we have a tail in the back is that it will generate lift force that will have a moment about the CG of the aircraft. So it will balance the moment about the CG. So the aircraft will not pitch up or down. I can do the same with a canard. except that it has to generate the lift on the other direction. So if I have a tail in the back, generally it generates a force downward. So the force downward tend to rotate the aircraft nose up. I can do the same if I have a canard which generates a force upward. If it generates force upward, it will rotate the aircraft nose up. So think of canard as a stabilizing surface exactly like the tail. But this one, the force on which is upward. On the tail, it has to be downward, and they will do the same effects. Okay. Now we said if I have a tail here behind the wing, it will suffer from downwash because the air is going downward. What do you think this canard will suffer from? Would it suffer from downwash? No. The canard is in here, in front, right? So in front in here, air will start to move up a little bit because it prepares to go around the wing. You see here, it starts to move upward a little bit as it goes around the wing. So canards will have what's called an upwash, just like you have a downwash here. So any surface in front of the wing will be subjected to an upwash. Anything behind the wing will be subjected to downwash. Okay. Here, increase of an angle of attack. Here, a decrease of the angle of attack. Okay. So that's for the downwash and upwash. Okay. Any questions so far? Okay. Now, what would the three-dimensional effects do with the value of the CL? You've mentioned that it will go down. Yes, but how would it go down? We need to quantify that. We need to put that in numbers. If you look at an airfoil, and those of you who have textbooks can open your textbook to Appendix C at the back, where you're going to see similar curves to what I have in here for different airfoils, where you see CL versus alpha. It's almost a straight line that has a slope. And typically, for most airfoil, this slope is about 2 pi. If you calculate, if you pick any airfoil from the appendix and you calculate delta y, the change in CL, over the change of angle of attack, you will find it that's almost 2 pi when I'm talking alpha in radians. That means 2 pi, what's the value of 2 pi? About 6.3, roughly 6.3. So the slope is 6.3. That's because it's an airfoil. If it is a wing, a finite wing, then the slope will be less than the 2 pi. That straight line will not go like this. It will go shallower. It will go like this. The slope will be slightly less. How shallow it will go will depend on how finite the wing is. So you should expect this slope value, A naught here is the slope of the CL versus alpha. You should expect that slope value to go down a little bit if the wing becomes finite. Okay, and that's why we had, and you had in aerodynamics in AE 220. So I'm just going to present the result here. We had a set of equations that would relate the slope, the CL alpha slope, to the slope of the airfoil, the 2 pi. This, you not think of them as typically 2 pi, the slope of the airfoil. So as the aspect ratio decreases, that means the wing becomes more finite. As this ratio decreases, what will happen is that this value is going to decrease. As it increases, it's going to increase, and so on. Okay, so aspect ratio is the single most important parameter, AR, aspect ratio, that affects the A. I hope we all remember what's the aspect ratio, which is aspect ratio. شباب. What's the aspect ratio?
I don't quite remember, but I think it's relating the length and the width. I think
Yes,
it's the
yes. It's in a sense, it's relating the length of the wing as well as the chord or the width, if you call it so. aspect ratio for a rectangular wing is exactly what you've said. It's the span over the chord. But that's only if it's rectangular. If it's not rectangular, like most wings, it's B square over the area, the span square over the cross-sectional area, over the planform area of the wing. B square over S. The length, if you call it the length, which is the span of the wing square, divided by the planform wing area, B square over S. Okay. An airfoil is essentially a wing with an aspect ratio of infinity, right? The span is infinity. Okay. As the wings get shorter, they get less aerodynamically efficient. So the equation that we have here says as aspect ratio decreases, that means the length or the span of the wing decreases, then A will decrease because this is the denominator on the denominator. It's on the top. So this one will decrease from the 6.2. Now, I keep on saying numbers because I want you to develop a sense of these numbers. So we all now know that the slope of CL versus alpha is around 6 something. 6.2 for airfoil and less than that for finite wing. Why would the slope be important? Because if I multiply that slope by the angle of attack, I will get the lift coefficient. If you multiply this slope by the angle of attack, you get lift coefficient. If you multiply the slope of a line by x, you get the y, right? So if you multiply by the alpha, you get the CL. Now, the relationship that relates the finite wing slope to the airfoil slope is different from one flight regime to the other. It's different if we are flying very low subsonic, just like in takeoff and landing, it will look like this, or if we are flying subsonic but not very low, in what we call the compressible regime, where air is fast enough that the wing will start feel compression of air, increase in density of air in front of it. So we call this compressible flow. So the relationship is different. And it's totally different if the air is moving at supersonic speed, where the wing doesn't get accustomed to the air. It doesn't see the air slowly as in here, it just gets shocked with the air. So in this case, the slope has a totally different relationship, 4 over Mach square minus 1. You see here the relationship does not depend on the aspect ratio. It really doesn't depend on whether the supersonic wing is long or short. It doesn't depend on the airfoil, because the airfoil is what determines the A0, the slope of the CL versus alpha. So for a supersonic wing, the slope between the CL and alpha is a number determined only by the Mach number. Okay, and it's per radian. I understand that maybe I don't have appreciation of the numbers. So let's see an example that will tell us what does these numbers mean. Okay, let me get that figure here. I will need it. Maybe it would be better if we have that. So that I can answer your questions over there. And let's put it in here. I don't need all of that. Let's just make it smaller. Okay. Let's read the problem. Calculate the lift coefficient for a high aspect ratio straight wing. So it tells me it's a high aspect ratio straight wing with a thin symmetric airfoil at an angle of attack of 6 degrees in a supersonic flow. So it tells me the flight regime so that I can know which equation to use. Okay. Now I don't want you to memorize these equations, of course. These equations, if needed, will be provided in a formula sheet or something, but I need you to know how to use them and what's the physical meaning of each. So supersonic flow, That means CL alpha, or the A here, A is the CL alpha. The slope, what the A is the slope of the line, is equal to 4 over root square m square minus 1. If the Mach number is 2.5, then this will give me 1.74 per radian. Now, I don't have a feeling of that number. Is it a high number or a low number? What does it mean? The slope is 1.74. This is just math. But if we start to write it in degrees, we will start to develop a physical meaning of that. What does it mean 1.746 per radian? It means if the angle of attack increases 1 radian, CL will increase by 1.74. It doesn't have a unit, of course. CL doesn't have a unit. 1 radian increase in alpha means 1.74 increase in angle of attack. We don't quite grasp the physical meaning of radian. Let's go by degrees. So in order to convert from radian to degrees, the conversion factor is 57.3. So if CL will increase 1.7 for every radian, it will increase 1.74 divided by 57 for every degree. That means 0.03 per degree. What does that mean is, if you increase the angle of attack by 1 degree, CL will increase 0.03. You increase it 2 degrees, it will increase 0.06 and so on. That's CL. Okay. So if the angle of attack is 6 degrees, the CL will increase 6 times 0.03, that means 0.18. So that means the lift coefficient, that's the final answer here. The lift coefficient for this wing will be 0.183 when the angle of attack is 6. Is this clear?
Doctor, what is the 57.3?
Oh, it's that, you see, if I ask you 1 radian equal how many degrees? How do you find it?
180.
It's 180 over 2 pi, right?
Yeah.
180 over 2 pi is 57.3. Okay, so think of it as the conversion from radian to degree. So if CL increases by 1.7 for every radian, it will increase by 0.03 for every degree. Okay, so that the increase will be 0.183 per radian. CL will be 0.183. Now CL is an important factor for me as a designer, because if I multiply it by 1/2 rho v square and then the area of the wing, that should equal the weight in case of cruise. So I will need these values when I start determining the wing area, for example. Okay, any questions? Okay. Now there is another set of equations, the same thing for the incompressible, low incompressible, high subsonic, and supersonic, but for the cases when the wings are not high aspect ratio, low aspect ratio, short wings, like for most military aircraft or fighter aircraft, I would say, they have low aspect ratio wings. And when we say high or low, there is like a rough number by which people use to determine high or low aspect ratio is 3. Okay, so if the aspect ratio is less than 3, it's considered low aspect ratio wing. If it's more than 3, it's high aspect ratio wing. Okay, so all transport aircrafts, I would say, Boeing, Airbus, all these have high aspect ratio wing because the aspect ratio is definitely more than 3. Okay, very few aircraft would have a low aspect ratio wing, like military aircraft, for example, like this one in here. If you calculate the span from here to here, square, over the wing area, probably it would be 2.8, 2.5 for this aircraft in here. So that's a short aspect, low aspect ratio wing. For low aspect ratio wing, aerodynamics is different. So the relationship between the 3D wing and the 2-dimensional wing is different. So let's one, it's going to be something like this. So the equations are going to be slightly different. This is for low aspect ratio. Okay, but the concept is the same. Only the aspect ratio would affect these for incompressible and compressible as well as supersonic flow. Okay. Moving on with the 3D configurations, we are done with the finite wing. If we want to add a body to the wing in this case, and I'm gonna jump to it because we discussed it last time. Some of you asked the question, what about the fuselage that we have in here? The fuselage will add some lift to the finite wing as well, but it was found that the lift of that fuselage is almost the same as the lift generated by the part of the wing inside the fuselage. So people said, let's take that fuselage out, let's remove it, and replace it with the part of the wing inside the fuselage, so that we study only one part, which is the wing. Now, that's not very accurate, but it's reasonable for initial design. When we design the wing by itself and finish its design, then we are going to start designing the fuselage and putting it there, taking this part of the wing out and adding that part of the fuselage and calculating the lift for the wing body combination. Okay? But it's reasonable to start designing the wing. So mostly aerodynamic design of the aircraft is the design of the wing. Fuselage in many cases is not designed by aerodynamics only. It's designed by what exactly you want to put inside it. What determines the dimensions mainly of a fuselage is the number of seats, the number of passengers, the number of lavatories that you have inside, the cargo that's going to be carried, if you're going to carry any fuel, the landing gear that's going to be retracted. That will determine the size of the fuselage. But the aerodynamics is mainly determines the size of the wing, not the fuselage. Of course, the fuselage has to be aerodynamically clean. We have to check aerodynamics of the fuselage, but that's after the initial design. Okay. Talking about drag, we talked about the skin friction drag as the pressure drag last time. We talked about laminar flow versus turbulent flow versus transition flow. Let me see if you remember what we have mentioned last time about the type of flows. Which of these two types of flows, laminar flow and turbulent flow, have a higher Reynolds number?
Turbulent.
Turbulent, of course. So laminar flow will have a low Reynolds number. The flow is well organized. It goes in layers. Once you have a higher Reynolds number, the flow will start to go into transition, and it will not gonna be organized. Then it will have a sense of organization, but it still is gonna be moving in various directions. But it will have a thick velocity profile, as you will see. Turbulent flows are good in sense that they tend to make the flow stick to the surface. Okay, although laminar flows are good in sense that they reduce the drag on the surface. So we have what we call laminar flow airfoils, and we have a fuselage flow is mainly turbulent, for example. So both of them are used on the aircraft. Both of them are good. They have some desirable and undesirable effects. Okay. The pressure drag is the last type of drag that we have, which is generated by the flow separation. If you have air sticking to the surface all the way to the end, which is ideal case, we will never have pressure drag. But in reality, at some point, as the flow starts to have what we call an adverse pressure gradient. What do we mean adverse pressure gradient? A resistance as it moves above the airfoil. At some point, it will not be able to stick to the surface and it will just separate. The layer adjacent here will have to move up because of the lot of resistance that we're having here from the circulating air in the back. This generates what we call a pressure drag. Okay, so pressure drag is generated by the wake of the wing at the back. Pressure drag is the main reason why we have a tail cone in the fuselage. If the fuselage ends abruptly, suddenly, as a straight line in here, I will have a lot of pressure drag. I will have a lot of separation. But the fuselage is generally has a cone in the back in here, so that flow stays attached to the fuselage as much as possible before it separates, and thus reduces the pressure drag. Okay. So all these parameters we have to keep in mind once we start designing the aerodynamics of the aircraft. We have wrapped up today and on Monday, we wrapped up the aerodynamics. Next week, inshallah, we're gonna summarize the propulsion characteristics that we will need. And in week 4 and 5, we will finish the control part that we will need, and starting week 6, inshallah, right around the midterm exam or close to the midterm exam, we will be starting our design problems. We will put everything together and see, okay, now we know this, we know that. If I want to design a 6-seat aircraft that will have a certain range, go to a certain altitude and so on, what should I do? So we're going to start the design by week 6, inshallah. Any questions, Shabib?
Yes, Doctor.
Yes.
It's maybe a little bit, it's unrelatable to the lecture, but I just wanted to ask, do you recommend the book in Arabic, أساسيات علم الطيران, أساسيات نسبة الطيران فضاء?
You mean in the for the lecture? Well, think of it as a help if you have a problem in translation. But if you don't have a problem with the English version, then it shouldn't be a problem. Okay?
Yeah, but I mean, do you recommend it as a source of revision? I mean, if
No. The textbook is enough. No, the textbook is enough. The textbook is way enough, because it's basically the same thing translated in Arabic. It was meant for those who have a problem maybe with the definitions, nomenclature, prefer reading in Arabic, but no, the textbook is enough.
But for someone who prefers to read in Arabic, it's...
Yeah, if you prefer to read in Arabic, that will help. That's the only thing that you have in Arabic. I mean, the textbook is in English. Yeah, but for the course, the textbook is enough. Okay. And I hope the remainder of you will get the textbooks from KFPM soon. We'll be assigning homework, inshallah, next week on Monday, and you're going to have a week to do the homework. Then we're going to have our first quiz. So we're going to go homework quiz, not counting the week of the midterm, inshallah. And by week 7, let's see how things will evolve. Inshallah, things will be better. And if that's the case, then maybe there is a chance that you guys are going to come here and we're going to have our midterm physical exam. Otherwise, we'll see how KFPM arranges for
the
online.
quiz will be on Wednesday.
Quizzes are typically going to be on Wednesday, yes. Okay, I will announce that, of course. You will have announcements for the due dates for the homeworks as well as the quizzes on Blackboard, inshallah.
Okay.
Okay.
دكتور يعني خلصنا chapter 2 on the textbook or not yet?
صحيح.
Now we finished chapter 2 يعني.